Good afternoon. Today we have gathered for webinars event series organized by eDiscovery and Tiscon. I think this is a very great initiative for the fraternity as a whole. My topic today is earthquake resistant design and construction. Before we begin the overall presentation about the topic, let me just put something for people who are not aware of what earthquake is. Earthquake is basically movement of earth crust or tectonic plates. As we all know, we are made up of different large tectonic plates which are called continents, and they are moving with respect to each other constantly. And when these plates collide or when these plates slide against each other, they release a lot of energy. As a result of it, the ground shakes and the event called earthquake happens. Structures are very much affected by the earthquake forces, and there are lateral forces or horizontal forces that act on the structure due to earthquake, due to its own weight. Important factors related to buildings and earthquake are the soil strata in which the structure is supported and the soil strata through which the earthquake waves pass. Also, the type of building material, so it's wood, steel, concrete, that matters, and proportions of the building, or what we call the structure of the building. How exactly earthquake affects the structures? If you can see on the screen, there are three images. First image is showing stationary structure which is standing on the ground. When the movement of earthquake occurs, the foundations of this structure shift. When they are shifting, the upper structure is actually trying to stand still because it is not still experiencing the earthquake. When the structure reaches the earthquake stage, the upper structure also starts moving, but by that time the foundation is started moving back because it wants to come to its original state. The ground is shaking, and due to this, the vibrations of the building start, and what we call the lateral forces or the horizontal forces, because of the weight of the structure, start acting on the structure. And this is a very critical event in the life of structure. As we all know, earthquake lasts only a minute or a half, or maybe 2.5 minutes, but its effects are far long lasting. So in India, according to the experience, past history, and understanding of whatever we have from geotechnology, there are 4 zones mainly in which the India's map is divided. You can see the zones over here. The blue zone indicates zone 2, which is the lowest intensity of practical earthquakes that we can consider. Yellow is zone 3 and green is zone 4. And all we know, the northeast belt of Himalaya or the region of Bhuj, which experienced earthquake recently, they are in zone 5. Zone 5 indicates the highest seismic zone in India, whereas zone 2 represents the lowest possible seismic zone in India. Earthquake is in structures. Why? Simply because human life is priceless. Property is damaged, yes, but human life is priceless, and that is what we should strive to save. You can see an image here, how the building has totally turned upside down, and I don't know whether people were staying in the building when earthquake happened, what would have happened to them. Here are some of the other pictures of earthquake which depict the types of buildings that get affected. Earthquake affects small, tall, all buildings. It is not that tall buildings are affected more or small buildings are affected more. Also, you can see the lower image where it is structure of water tank, overhead water tank, that is supported, and that is also getting damaged. So it is not necessarily that the residential buildings or the commercial buildings that get affected, all structures get affected because every structure has its own mass or weight. So when we start thinking about earthquake design, the first thing that we should start thinking about is architectural planning. Architectural planning. So the plans which are favorable in terms of having less effect of earthquake, that's what we are talking about. So when I say favorable parameters, it basically talks about how good the plan is to make a structure which is stringent enough or strong enough. Of course, so needless to say, regular planning, which preferably symmetrical, is the best suited because it gives lot of resistance of the building within the plan itself. Well-proportioned building. When I say well-proportioned, I say it's not too tall, it's not too long, it's not too short, all of it. So the building's design is a characteristic of the requirement. And the characteristic of requirement is captured by the size of the building, and most importantly, it should be well proportioned. Avoiding discontinuous continuities vertically as well as horizontally. So avoiding large setbacks, avoiding large cantilevers, avoiding heavy mass at the roof level, avoiding large atrium spaces, avoiding re-entrant corners. All of these constitute to a well proportioned or well planned building. Other important aspect of the planning is even load distribution. What do I mean by even load distribution? When your building is planned, let's say you have a hotel building and you have swimming pool, you have banquet roofs, you have banquet areas, you have large gathering areas. If all of these large spans, large loads are stacked in one side of the building as compared to other normal building, then it would lead to uneven distribution of load as well as structural system, which is not good for the building. Other favorable pointers which I talked about briefly, to avoid large cantilevers. Why? Because large cantilevers affect not only horizontal motion, also horizontal motion, also vertical motion, and that is detrimental to the joint of the column and beam. Atrium spaces. If you have large atrium spaces, your diaphragms are weak. Diaphragms are what we call slabs. Slabs help distribute the earthquake forces within the structure. With large atrium spaces, your diaphragm become weak. Hence, it is not good to have large diaphragm open spaces. Avoid open stilts. We'll see some of the photographs later where what happens we have open stilts. Avoiding floating columns. Now, I know most architects will preferably not have floating columns. It is not desired. Everybody understands it. But we still need to have floating columns because of some necessity. So, when I say avoid, it does not mean it cannot be done. It just means that keep it to a minimum so that every structure can be made as stable, as simple as possible. So here are some graphical images of how architectural planning might affect. You can very clearly see first image is of a large building tower with a podium. So there is a lot of discontinuity of mass as well as stiffness when we go up. Similarly, a L-shaped building, elevation point of view L-shaped building. Again, you have some story which is very stiff or very large compared to that upper story is very small. It again, builds complicities. The third image on the right hand side top is basically with large cantilever decks at roof level, at the highest possible level where the mass is, and it is not good. Flexible stories, so you have either open stilts or very tall stories, at lower levels somewhere. That brings flexibility into place. So when it becomes flexible, it becomes weak and it is likely to sustain more damage. So all these, of course, all of them are, based on need to basis. Some of them are required as a part of functionality, but the lesser we have, the better it is. Shapes, when we talk about shapes, plus shape building in plan may be architecturally very wonderful, but it poses its own structural problems. We'll discuss later perhaps. L-shaped buildings in plan, similar, it causes torsion. What is torsion? We'll see sometime later. But all of these are, if possible, avoid kind of situations. These are some of the images of two taller buildings. So first building on the left hand side is tall. It's not just tall, it is too slender. The height to base ratio is very, very small. That's why it's too tall. Second building on top is too long. So it will basically have too much of stiffness perhaps, and it might not be serving good for us. The third building is too large in plan in both directions. Again, it will have its own set of problems. So as I told you earlier, short buildings not necessarily are safer. It's just the way they are proportioned. Once architectural plan is available to a structural engineer, his job is to provide a safe and sound system. That stems from structural scheme. Structural schemes, the first choice one has to make is a choice of material. So it could be concrete, it could be steel, it could be wood, depending on what suitability it is. It could be composite. Second thing will be the planning of vertical elements and the load distribution elements, what we call columns and beams. So planning of columns, arrangement of columns forms one of the most important aspects of structural scheme, because it will define the stiffness, it will also define the load path, and it will define whether we need floating columns, we need shear walls, we need other supporting. So planning of columns is very critical, and it should be the most important aspect of scheming. So when we receive architectural plans, we need to sit down, understand how the space moves vertically, how the space moves horizontally, and look at the structural system which preferably goes through and through. Shear walls are key elements of earthquake resistance, and they need to be planned carefully. It is not necessary or it is not important to have shear walls everywhere possible. It is important to place them well, it is important to make best use of them so that we maintain best symmetry in structural system even if it is not in an architectural system. Other important path which is I touched upon earlier, avoiding discontinuous load paths. So when we have load paths, what do you mean by load path? When basically floor slabs transfer the load to the beams, beams transfer the load to the columns, and columns down to the foundations. But at times when columns cannot go all the way up to the foundation because of lobbies, because of high level spaces, or because of spans that are required below, these create alternative load paths, and you have to support the columns on the beams or girders. So the lesser the percentage of those in the structural building, the better it is for the building, because this is something that is unknown. Earthquake today we don't know 100% how it happens. Earthquake today we don't know how the energy is dissipated. All we are doing is guessing in terms of how it happens, why it happens, and how we can best mitigate the risk. So it's all about mitigating the risk. So it's more important to know where the risk is. So the better the load path, lesser the risk. As simple as that. So these are some of the examples. Of course, these images are available on the net, they are available in the code. I'm just trying to highlight what I mean. So if you can see on the image, the right hand side, there is a dead wall, which structural engineer thought he will use as a very stiff element. Unfortunately, for whatever reasons, it cannot continue all the way up to foundations. Then hence, it is not the best system possible. Maybe it could have been placed somewhere else, it might have served its purpose. These are the images from the code which are very direct. You can see very clearly the top image has 3 columns going all the way up to down, but the one on the right hand side, for whatever reasons, the load path is changed, and this causes 2 critical points in the load path. Or if you see the lower plan, the plan is skewed. Does it mean the structural system should be skewed parallel to it? Probably no. So it is for the structural engineer to arrive at a scheme which is as symmetrical as possible and as systematic as possible. Similarly, if you look at the plan with shear walls, on the right hand side, you can see there are 4 shear walls placed on the 4 sides. Are they the best position? We cannot say. We have to see the 3D analysis. What I'm trying to say is it's not enough to place shear walls where they are available. We have to make the planning judiciously. We have to make the use of the shear walls effectively. So when we see any structural plan, as structural engineers, what are we looking for? We are looking for columns, column beam frames, shear walls, and coupling beams. These are our 4 main elements of design. It means that we have to make use of these elements for 2 reasons. One is gravity load system, which is the vertical load transfer, and a lateral load system, which is the earthquakes or wind. In case of earthquake or wind, as we all know, shear walls and shear walls with coupling beam perform best. When I say perform best, in the sense that they have the largest possible stiffness to carry the lateral load. Does it mean that they have to be placed everywhere? No. If you look at the plan that is chosen, it may not be the best possible plan because my cores are on one side of the building. And this is something that we need to try and avoid as far as possible. So that's why we came to the next aspect, or torsional behavior. For non-structural engineers, this may be something that is something weird, right? But for us as structural engineers, this is the most important phenomena that we need to cater to. Torsional behavior is detrimental for the building for various reasons. One, torsion of the building as a whole is something not well understood by us. It is neither understood by analysis nor understood by us in principle. Second, it creates additional stresses in structural elements where we don't expect them to have. it causes sudden failures because torsion will cause shear stresses in columns or in shear walls or sometimes in beams also. And shear stress, shear failure is a brittle failure. It is sudden. It will not give you any warning. It will cause a sudden failure. Other aspect of torsion is for every vibration or every oscillation, it will keep on increasing the intensity or the amplitude or the magnification. And that's why torsion is something that we don't want to have. Third and last and the most important aspect is the cascading effect. Now what do I mean by cascading effect? Suppose we have a structural system and there is always some redundancy in the system. If one of the column reaches its near failure load, it will start slowly giving away. What happens to then? Then it will transfer some of its effect to the neighboring columns or neighboring walls. They will come into play. They will go and start going near the failure location. And this is cascading effect. The structure will start going into local failures one by one and might trigger a complete collapse. So this is a graphical representation of torsion. One can imagine a child on a swing. If he is sitting properly in the center and he starts swing, the swing will go in the same line, straight. But if he sits on the one corner and starts swinging, the swing will start not only going forward and backward, but also start twisting. And the same thing, believe it or not, happens in buildings. So why will torsion happen? So let's look at some graphical images. The image below the swing indicates that the building is fairly regular in terms of its arrangement, rectangular. But it has heavy mass on this side and perhaps not so heavy mass on this side. This will cause torsion. So the heavier mass will start giving more and more forces in each oscillation and ultimately the building will go in the torsional mode. Or in this figure you can see the local open story over here, which means there is not enough stiffness because there is no walls in that local position. Again, it will lead to torsion because the stiffness is on this side and my mass is on this side. The third building, you can see the core is eccentric. This is the core. And the entire structure will vibrate around as if it's a pivotal point of vibration and it will start going into torsion. So this torsional behavior is something that will come through us from analysis and we need to study it, make all the possible efforts to avoid torsion or to keep it to a minimum. That's where we come to structure design parameters. What are the parameters we choose for design of buildings? Very important aspect is foundations. And for that, geotechnical investigation is a must. We need to know exactly what kind of soil we are expecting, what kind of support capacity we are expecting. We also need to understand to what level we need to go in terms of depth, all of it. And based on all these parameters, we should choose an appropriate foundation systems. Now I know in villages, in remote places, there is one contractor who does everything. Architectural planning, design and construction. He may not have all these things with him. He uses his best judgment, he uses his experience. But perhaps that is where the problem starts. So at least for us who are educated, for us who understand what engineering is, we should take efforts and guide those people properly. Using appropriate zone factor. Now as we saw a map, there is map which sort of graphically shows where the zone 2, zone 3 are. The boundary is not marked on the site, on plan. If you go on site, the boundary may be passing through the site. Whether to go for zone 2, zone 3, choice from cost point of view will be to go for zone 2, but from safety point of view, you might be better off sticking to zone 3, which tells us that we have to make judicious choices when we start designing. Use of appropriate importance factor. Importance factor is something which is our choice as structural engineers. If we feel the building has, let's say, pharma plant and the chemicals that are there stored may be dangerous. In case of event of earthquake, the chemicals might come out, they might get loose, and if it affects the health of other people around, it is worse. So importance factor could be 1.5 or even more if you want. So choice of importance factor, apart from codal guidelines, again is a measure of your understanding of how the building should be treated. Choice of lateral load resisting system. This is very, very classic. uh, all of us tend to first arrive at system which will give us proper gravitational load flow. Not always we think of how it will also prevail laterally, and that is where the choice of lateral load system comes into play. As we saw, we have to make judicious calls. We have to choose which columns, which walls are my most logical placed elements which will help me support my earthquake. And those things you make stronger. Don't have to do everything strong, you don't have to make everything weak. You can choose, and that's the best part. As structural engineers, we can make alternatives, we can arrive at things that are best suited for the building. Third, but last, after all this, once we arrive at loads, once we arrive at sizing, once we arrive at finalizing this loads, load paths, all of it, the sizing of members, that is most critical. So again, when I mean sizing, architects always complain about higher column sizes. That's why we try to squeeze column sizes, maximize concrete, maximize reinforcement. Does it always work for us? May not. So that's why we have to again look at how best we can suit both the requirements. Maybe you need to have another column just to avoid the overall increase in size. So things to look at will be, we might have to do one or two iterations to arrive at final structural scheming. Very often people ask, the other building is only 4 stories and it has only so many walls. Why do you require maybe 5 walls more than him? And something that all of us should understand, every building behaves differently in the same zone, even if it is neighboring building. If the structural system is different, if the architectural planning is different, it will have totally different behavior. It does not matter whether you have the same area, whether you have same number of floors. If your system is different, the behavior is different. In that sense, every building is unique. You need to identify what is unique to your building and treat it best. That's all as structural engineers we can do. So this just graphically shows this figure. When the 3-story buildings actually become more critical than the taller buildings. So why it happens? Because 3-story buildings are actually stiff. They don't have that much capacity to vibrate or dissipate energy as compared to tall buildings. So in case, there is, as structural engineers, we face these comments or queries from architects or clients saying, why are you using so many walls? Why are you using so many stiff columns or whatever? So as long as we are convinced that we require this, we should stick to it. We should make proposals and we should convince clients that this is the best system for the given structure. Remember, for every structure it will require its own system. What are the issues in terms of design that we need to look at? So let's say we have residential buildings which are long, and that's why we divide them into convenient long small buildings. When we divide them, we introduce something called expansion joint, and the expansion joint needs to be treated carefully. Very importantly, there have been instances where the buildings were too closely spaced and actually collided against each other, causing damage that perhaps would have been avoided if the buildings were slightly more separated. The buildings individually were designed better and could have survived earthquake better if they had not collided with each other. So when we are planning building, when we are planning expansion joints, we need to take care of this. We need to understand how close the buildings are going to be. Are the floors on both sides at different levels? If they are different, we need to be more careful. So that's where we come to some of the provisions of the new codes that have been released, 1893, 13920, which have been released in 2006. Now, most important thing that we should note here is earthquake is something that we are trying to understand better every day. It is not something that we 100% know today. It was not something that we knew it 10 years back. So if you see historical development of code of earthquake, perhaps before 1990, there was not much discussions in terms of how to calculate earthquake force, how to apply it in the analysis. There were no analysis tools available. In the era between 95 to 2000, we started getting better computers, we started getting better software for analysis, so we started understanding the behavior better. After that, the codes also got revised because Killari happened, Bhuj earthquake happened. These two codes forced us to understand or change the way we approach earthquake design. And that's why we should look at the provisions of the new earthquake code and understand that they have come from our historical understanding of our behavior of buildings, understanding of what earthquake force is, understanding of how it affects our building. So if you look at the new codes, you can clearly see the focus is shifted, or rather very prominently placed, on strong column weak beam theory. Column sizing now is based on stress level. It is not purely based on loads. It is not purely based on P and M character. It is also being based on stress levels. Why? Because it has been found that columns which are slightly oversized perform better in ductility. We'll talk about ductility a bit later. Beam column joint, that becomes very, very important aspect of the entire earthquake behavior. And that's why there is a lot of focus. We need to check shear, we need to check moment capacity at joint, we need to have adequate area at the joint, all of that. So that's why the provisions like minimum column width, minimum beam width, all of that have come into play. Importance factor based on the type of building and occupancy. So now this is new. Earlier, all earthquake codes were saying is that importance factor is only based on the type. So if it's a monumental building, or if it's a very important building like an institution building like a railway station or a hospital, it needed to be higher importance factor. But now there is a category added based on occupancy. Now why? We need to understand this, I think. Human life is priceless, as we saw. And it is not that the person who stays in a small building is less important than the person who stays in a high-rise building. It's just that likelihood of a smaller building collapsing completely before a person gets out is lesser compared to a taller building. That's why buildings which have more than perhaps 200 occupants today are required to have slightly more design earthquake force as compared to a smaller building. So they are not trying to tell you that you are less important. It's just that they are trying to make you more aware that you should pay more attention to whether people can get out safely within that 1.5-2 minutes. And very importantly, they have now sort of made mandatory the use of all advanced analysis engines. Why is that? Because earlier code, when they were established, there was hardly any penetration of computer as well as software. Today we can't say that. Today practically everybody uses computer, everybody uses tools. So whether it's a village, whether it's a city, engineers have the benefit of using those tools, and we should make use of those tools. But that's why they are making you use dynamic analysis, which gives us better understanding of our behavior during earthquake. Other things which were not so explicit earlier have become explicit. So floating columns cannot be part of lateral load resistance. It is common sense, now it has been put into practice. Flat slab structures, they have historically been brittle in failure modes. Please understand, all of this stems from the fact how building might fail. It doesn't have to fail. If it fails, if there is a brittle mode of failure which gives no warning, it is the worst. That's why flat slab structures have been categorized as the worst possible brittle mode failures. Accordingly, there are stringent parameters. So it is not that they have stopped you from using flat slabs. There are stringent parameters. You use those stringent parameters, you size your building properly, you can still use flat slabs. Similar to that, stringent provisions to avoid soft story effect. If you remember, earlier code allowed you to have soft story with a penalty in terms of higher design forces. Now the code committee believes that it is not sufficient to have that. It may not give us that safety. So they are basically making provisions, they have added provisions which will make you count, make you calculate the stiffness and avoid soft story. And it is very significant. It might be to an extent over stiff, but I think it is better to have a building that does not collapse than better to have building which is slightly costly. Member strength today in analysis is considered as a whole cross section, which will be reduced to crack section. Why? Again, because in earthquake or during earthquake or even before earthquake, some members might have developed cracks because of tension. These members will not have the whole section available for your design. And especially when earthquake starts, during the first few seconds, it will reach the peak response. And if there are cracking in columns or beams at that moment, then they will not perform the same for the next 1.5 minutes of the earthquake, and will not have the same kind of stiffness to offer, which has been recognized. It was always there in international codes. It's just that we have started recognizing it today and putting in the code today. and stringent provisions for all types of irregularities. So we talked about irregularities: stiffness irregularity, weak story, short story, heavy atrium areas, cantilevers, all of it. So all of them now have been treated as irregularity, and for all irregular structures we need to perform better analysis and better design. We'll just shift slightly from provisions to why these provisions would have perhaps been thought about. So if you can see these images, the image on the left hand side actually indicates a joint failure of a beam column joint. You can see the beam has actually practically come out of the column joint by rotation. On the right hand side, similar behavior of a column joint junction, but here the concrete is completely crushed. You can see that, right? So this is sudden failure and it is catastrophic. What we talked about, compounding of buildings, very classic photo. You can see the buildings on both sides have different story heights. Probably the buildings have performed individually good in earthquake, but because they were too close, they have actually hit against each other. Similarly here, you can see this building and this building. This part of the building is not absolutely affected. Also, perhaps here the damages are more local, but because they were too close, they hit each other and these junctions have given away. Now, do we want these? This is one of the classic failures of earthquake. That's where we talked about earlier, foundation systems. Now, this soil, we don't know what characters it was, but basically this happened because soil upheaval or soil liquefaction. So soil actually gave away completely and the building tilted as a whole. The total building tilted and collapsed. So that's why we need to have a better understanding of our soil foundation strata. And the classic photo of soft story effect. This is scary and I think it is important that we take it seriously. This is the upper building practically is intact, as you can see. And why? Because brick walls offer stiffness that we don't consider in analysis. But the lower story did not have brick walls and actually all the columns in the lower story simply collapsed. And this is one of the, if you recall Bhuj earthquake, quite a few buildings which came down in Ahmedabad and other cities in the Bhuj area were because of this soft story effect. And that is where the code has become stringent about it. Ultimately, it's all going back to human life. Human life is priceless, and as structure engineers, it is our responsibility to provide buildings that give chance for a human to come out safely. So some of the, coming back to provisions, so these are the provisions that we are talking about. So weak stories, less stiffness, less flexibility, all of it. So it's not important to have stiffness only at the base. You should not have heavy mass at top also, because heavy mass will at top will give more earthquake force at that level and which will affect the entire building. Or you could have a local soft story which might cause a local failure. Ultimately the entire building will come down because the mass will come down. This is something which is torsion related, and that we saw what torsion is. So you can see code has given us limits in terms of what we can allow as a non-torsion and what can be considered as a full torsion. So if you see in this build in plans, this plan has lot of re-entrant corners, and these re-entrant corners actually cause each wing to behave like a flap. If you recall, in the childhood we used to have those paper kites, and they will wave with the wind. It behaves actually like that. Or a L-shaped building will behave similar to that, because each of these legs are strong in one direction but ultimately cause torsion about the center. These are some of the examples of atrium areas. Now why atrium areas become critical? Because if you can see, the slab distribution will prevent the force traveling effectively from one side to the other because this slab is too thin. Or in this case, this structure actually gets isolated practically because of a large atrium opening around the edge. Now does it mean that we can avoid all of this? Perhaps no. Architects might still want this as a part of feature in the building. It just tells us that we need to be more careful about those structures.